So this is again going to be a long lecture, and what is my agenda of this lecture? I'll just detail it down. And what I want to for this lecture to be is about, I will cover about the resistance in series or parallel, which is the series and the parallel circuits. So previously we have seen the Ohm's law, we saw about current, we also solved the problems related to KVL, KCL, and we solved the problems related to Ohm's law. Then again I covered something about the vector, and all those was in the previous lectures. But this lecture I will solve more problems about the network theorems. After also I will solve one or two problems applying the KVL and the KCL. Then I will solve the problems using the DC theorems. So we are considering only the DC circuits. So in these DC theorems I have covered in detail in some of the previous lecture, but since I don't feel that those videos were much better understanding, since I've just recently I have switched to the whiteboard teaching by a new software which I am using here. So these videos would be for better understanding, and again I will try to cover this video in 20 to 40 minutes or even 15 minutes, and try to use this video for more problem solving. So the first thing which I want to say is about the Ohm's law, which we saw VIR, that is equal to V is equal to IR, or I is equal to V divided by R, or R is equal to V by I. So this was the Ohm's law, and the unit of the resistance is ohm. And again after that it's possible to connect many resistance in series. So there's 1, 2, 3 resistance connected in series, and the value of each of these resistance is R1, R2 and R3. And if you are connecting 3 resistance in series, and you can call this as a series circuit. So we are considering only resistance in this case. We are not considering other elements like an inductor or a capacitor. So I am connecting this full circuit to something like a source, which is a DC source, and this is a 10-volt battery, for just taking an example. In any case, this is a source, and current will flow, which is I. So when I am talking about the series circuit, what I find is that the current flowing through all the resistance or the elements will be same. So the current flowing through the R1, I will be the current which will be flowing through R1, R2 and R3 will have the same current. Again so the voltage drops across each of these resistors. So the current will flow through the resistance from higher potential to the lower potential, and the voltage drops VR1 can be written as IR1, and VR2 can be written as IR2, and VR3 can be written as IR3. So again the total voltage, if you are applying the KVL, so the minus V, there is a voltage rise here, and you are going from this from in this direction. So minus V plus VR1 plus VR2 plus VR3 will be always equal to 0. So V equal to, applying this, V equal to IR, which can be written as from the Ohm's law, and which can be written as IR1 plus IR2 plus IR3, by just replacing this into this equation. So one equation, if you can say. So what you are finding out, I am writing it in the top. So you're finding out that resistance, so all the I will cancel out. So what you're finding out is the resistance is R1 plus R2 plus R3 for the circuit, which is also known as the R equivalent. So again, being more specific, you can say that if you are having a series circuit, the resistance R of the circuit equivalent will be equal to the summation of all the resistance of the circuit connected in series, and again the total voltage will be equal to VR1 plus VR2 plus VR3, and the current through all the elements, that is I1 equal to I2, IR1 equal to IR2 is equal to IR3, will be equal to the I, and the equivalent conductance of the circuit can be given as 1 upon R1 plus 1 upon R2 plus 1 upon R3, that is the opposite of the resistance. So these are some of the things which you will need to take. So if there is any, so this is a full circuit which is in series, all the elements, but you will find that there might be sometimes a sub part of a circuit which is connected in series. So to find out that whether a circuit is all the elements of the circuit is connected in series or not, one of the ways to find out is that the current flowing will be the same through all the elements connected in series. So to just demonstrate that, if you are having a circuit this way, this is a resistance, then you are having multiple resistance here, and you are having multiple resistance here, and again you are having a resistance here, and this is connected to a voltage source, suppose 100 volt, and this is a 10 ohm resistance, this is R1, this is R2, this is 20 ohm, this is R3, suppose this is 20 ohm, and this is R4, so this is 20 ohm, and this is R5, this is 20 ohm, this is R6, suppose this is 300 ohm. So what I find is that this is my EMF. So my current is originating from here, and when it will, after reaching this point, so again this point you will have to consider the KCL will apply. So whenever what is this is my element. So individual resistors, or when you are considering the AC circuit, this could be a capacitor, it could be an inductor, so individual elements, even a source of DC, so this is individual things are known as elements of the circuit, and this is one element, and this is a second element, this is a third element, this is a fourth element, this is a fifth element, and a place where two or more elements meet are known as junction, or is known as a node. So this is a node in the circuit, and the current I, when it will come to this node, it will divide itself in two ways. It will divide itself as I1, and it will divide here as I2. So according to the KCL, or Kirchhoff's current law, the I will be always equal to I1 plus I2 in a circuit. But what you will see here is that the current flowing through these two resistors is I1, and the current flowing through these two resistors is I2. So you can say that since the current is flowing through these two resistors are same, you can simply say that the R2 and R3 are in series, and it can be written, so R equivalent of this total branch can be found out as R2 plus R3, and in similar way this two is in series, so the R equivalent of this can be found out as R2 R4 plus R5, and again when there is a division of current, so the elements through which the currents are directly divided, you can say that this is in parallel. So the R equivalent you found out, and the current coming here from here is I, and the current leaving here is I, but it is dividing itself as I1 and I2 here. So these two elements are in parallel, and you will have to apply the laws of solving this equation parallelly to solve it. So again, next we will see what parallel circuits are all about. So going in detail, considering that there is 3 resistors, each of them are connected in a parallel way. So this is a resistor R1, this is a resistor R2, this is a resistor R3, and when I'm connecting this to a source, so the current will be I, which will be flowing, and this current will divide itself into I1, it will divide itself into I2, and it will divide itself into I3, and this is a node, and these are my individual elements. And if you say this is a loop, something known as a loop. Again, if you are moving this, you are starting from somewhere and you are coming to that place back, then that is known as a loop. Again, you are starting from here and it's possible to come back to this place, so this is again another loop. So what I am doing is that this is my voltage V. So the current I has divided itself in such a way that I is equal to I1 plus I2 plus I3, and this is by applying the KCL. And my when I am applying the KVL to this circuit, what I will find is, if I am going through this way, the first loop, and this is a second, and this is a third, what I will find is minus V plus I1 R1 equal to 0, and minus V plus I2 R2 equal to 0, and minus V plus I3 R3 equal to 0. So my V equal to I1 R1, my V equal to I2 R2, and my V equal to I3 R3. And what is my V? Is my voltage. So I can put my I1 as V by R1, my I2 as V by R2, and my I3 as V upon R3. And when I will put that in the equation of this, and my I is equal to V upon R equivalent in this case. So my V upon R equivalent equal to V upon R1 plus V upon R2 plus V upon R3. So that's how I will, if I just writing it here, so my 1 upon R equivalent equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. So that's how I have found out the equivalent resistance, which if I take reciprocal, I can write R equivalent is equal to R1 plus R2 plus R3. I cannot write that, but 1 upon R1, that's how you will find. So just simply writing it up, what you would have found out is 1 upon R equivalent equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3 for a parallel circuit. So if there was only 2 resistance, then you can return it as 1 upon R1 plus 1 upon R2. So this again, if you are solving this, will call R1 into R2 is equal to R1 plus R2 is equal to R equivalent. So you are taking the reciprocal of that, and that's how you are finding the resistance or equivalent resistance in parallel circuits. Again, one more thing was that the total current was equal to I1 plus I2 plus I3 in this case, which was the individual current for the resistance R1, R2 and R3, and the voltage across each of this resistance was same. That is, the voltage was same across each of this resistance. V1 was V into R1, so V1 equal to V2 equal to V3 was equal to V. So if there is a branch and I'm having two resistors which are connected in parallel, and the voltage across this branch is V, then the voltage across each of this individual resistance R1 and R2 will be also V. So that's what we have found out. And the current will divide. Suppose this is a current, this is I1, this is I2. So the current I is equal to I1 plus I2. The current will divide itself, and you found out the equivalent resistance R equivalent as 1 upon R1 plus 1 upon R2. And this is some of the things you have considered for solving the series and parallel circuits. So this is only considering the DC circuits with resistance, and the same laws can be applied if you are solving it for the inductor or a capacitor. So I am not considering the inductor and capacitors in these lectures, and when I will be solving for those in the AC circuits, I will consider that. Now, after considering the series and the parallel circuit, one of the important steps is defining the different electrical. So what we saw was about the series and parallel circuit, and next what I will, before going to solving the network theorems, also problems related to KVL and KCL, I will simply say use some of the different symbols which I am using. So this is a symbol of a resistor. So this is how you can represent a resistor, and usually the battery is represented in this way, which is could be a DC source, and this is a higher potential side and this is a lower potential side of the battery. So this is what is for my source, which is a DC source, and if I'm having a capacitor, I can represent it like this, and the representation of the inductors are usually this way. And then if I'm having an ammeter, then I can represent it this way, and if I'm having a voltmeter, I am represented this way. The voltage, the variable resistance is usually represented this way. So these are some of the basic circuit representations which you can find in most of the, while solving most of the problems. Again, earth can be represented this way, and sometimes is also represented in this way. So I will use these notations for solving the problems. Also, you can find it useful if the same is being used in your books or while you are solving the problems. So the next step is what I will call is the application of KCL and KVL. So KCL is very simple to apply, and we have seen that previously, and again I will just simply show you how to apply the KVL in a circuit. So if I am having a simple circuit here, I am taking the case where there is R1 and R2 is a two resistance, and you are having a voltage V. and this is a rise in voltage I am considering, and first you have to, and the I is a current. So while we are applying the KCL, you have to go through a closed path or a closed loop. So you have to start from a point. So if I'm saying I'm starting from the point which is a voltage V, and I'm going in a closed path through this loop, so I will have to come back to the voltage, and the current in my both the resistance will be I, and there will be a voltage which drop across the resistance. So resistance is the element which will usually cause some of heating, and for each resistance there will be some kind of a drop in voltage which will be happening. So if I'm saying that the VR1 is the voltage drop in this resistance, and VR2 is the voltage drop in this resistance, and this is my plus and this is my minus, so voltage drop will always happen from a higher potential to a lower potential. And one of the way to write the equation is that you'll have to decide what you are going to do. So first I'm going to decide that I will take the rise in voltage in my circuit as negative, and I will take the drops in potential or voltage whichever I comes across, voltage drops in my circuit as positive. So I'm having a minus V here, and when I'm moving, this is a voltage rise. So this is from the lower potential to the higher potential I'm moving, and this is a voltage source, and this is a voltage rise which I'm coming across. So I'm taking it as a negative, and this is a voltage drops which I am coming across. So plus VR1 plus VR2 is equal to 0, and again I am writing that from the Ohm's law. If I am writing that, then I can write it as IR1 plus IR2 for each of these individual resistance. So again I can take V equal to IR1 plus IR2 equal to Z equal to V equal to, so this is the one equation which I have got, and I have got this equation by applying the KVL. So again there could be complex ways in which complex circuits in which you could want to apply this, and again simply you can say that this was my circuit and we have applied the KCL multiple times. So taking a simple example of a circuit, this is a V equal to 100 volt, this is a R1, this is a R2, this is I, and this is I1, this is I2, and if I take this as I, then this is what is called as my node of my circuit. So node is a place where two or more elements are meeting. This is one element, this is one element, two or more elements are meeting in my circuit, or two or more branches are meeting. So this was a branch, so a branch. So again you have to find out a node, and the current entering the node will be always equal to the current leaving. So the current entering was I1, so I and I will be always equal to I1 plus I2. So this was my KCL. So just solving more problems. So this is my circuit. This is the first problem to solve, and this is my circuit where I am having a 100 volt source and a 200 volt source. So I am having two sources. I am having a resistance which is R1, this is a resistance R2, and this is a resistance R3. So what I want to find is, I want to find the value of the current I, which is equal to I1 plus I2 using the KCL, and to find out the value of I is my task. So the first equation which I get in this, the first equation which I get is like I is equal to I1 plus I2 by applying the KCL to the circuit. And then again there is a two loops in this circuit. This is a loop 1 which I can go through, and this is a loop 2 which I can go through in this way and this way. So by going through the first loop, what I find is there is a fall in the potential here, and there is a rise in the potential here. So I will write for the rise in the potential, for the fall in the potential I will write 100, and taking the minus sign, and minus again we are moving in this direction. So and the current is, so if you are going in this direction, and if you are going in this direction, you're coming back, and again this is the direction of the current. So again this is a rise in the potential in that case. So this is 100 you will put, and you will put I1 R1, and if you are going in this way, plus I R3 equal to 0. This is the second equation, and going for this loop there is a fall in the potential here again. So minus 50 or plus 50 plus I2 R2 plus I R3 equal to 0. So this was my first equation which I got, this is second equation, this is third equation. Now the full idea is what I need to do to solve this equation. So one way to do that could be to just find the value of I for the circuit. So again that's not very much possible here to solve it in series parallel because you have voltage source here. So now what you will do, you would be thinking, and the best possible way could be to bring both these equations in a form where you can convert it into one of the quantities. So if I'm writing this, I'm bringing this, substituting the I here, or bringing this both equations in the form of I2. So my I2 is equal to I minus I1. So I'm putting it here, so minus 100 plus, or my I1 equal to my I minus I2. So putting it here, so I will get my R1 is 10 into I minus I2 plus I R3 is 10. So that is equal to minus 100 plus 10I minus 10I2 plus 10I equal to 0. So that is minus 100 plus 20I minus 10I2 equal to 0. So this is the one equation again which I have got. And now again the first equation which I solved, and for the second equation or for the third equation, again doing the same thing, which I will get 50 plus I2 into 30 plus, again substituting the value of I, will get I into 10 equal to 0. So now you have got two equations, and from this equation you can easily get the value of I2, or you can easily get the value of I, and you can substitute it here. So that's one way to solve. So I will just, so now just simply writing the two equations which we got from here, so after solution from here and here. So I'm solving the first equation and or the second equation here, which is from this, and when I'm solving this I'm getting the value of I2 as 2I minus 50. So if I write this as my third equation and I'm putting this in the first equation which I have got, so this is essentially something like your fourth or fifth equation if you are going in the sequence, but to simplify I've written it as 5. So going in the sequence, if I'm substituting this, then 50 plus 2i minus 50 into 30 plus 10i equal to 0. So this is my 50 plus 60i minus 5 3s are 1500. We are multiplying that plus 10i. So to solve that further, what you get is something like 1450 plus 70i equal to 0. So my 1450 or minus 1450 equal to 70 minus 70i. So my I in this case is equal to 1450 divided by 70. So if I do that calculation, I will get my I as close to 20.75 amperes. So that's how I have got my I. So again my I equal to I1 plus I2, and if I am substituting this value of the I in this equation, I will get the value of I2. So my I2 could be something like 2 into 20.7 minus 50. So taking this approximately close to 21 for just simplification, if I do that, if I get close to 42 minus 50, so my I2 is close to 8 amperes, could be something 7.8, and my I1 plus I2, so just wait a second. The correct value of I2 is close to 8.6 amperes. So this is what my value of I2. So my I equal to I1 plus I2. So my value of I is 20.75, which is equal to I1 plus 8.6 amperes. So I have found out what was question was. My question was only to find out the value of the I, which I have found out as 28.7. But again, to further do that, further find out even the I and I1 and I2, I can do that simply, and so my I1 will come close to 12.15. So this was a simple example of a circuit which was being solved by using both KCL and KVL. So we did not apply any series or parallel simplification here, but by using both KVL and KCL, it was become possible to find out I1, I2, and even the I1 plus I2 currents in all the branches. So there's multiple ways to do the same thing, and you can solve using the multiple equations, but this was one of the ways which I just demonstrated how you could do this. So the next kind of analysis for solving the circuits is also known as a loop analysis or mesh analysis. So by considering the same kind of a circuit, you are having a voltage source, You're having another voltage source. You're having a resistance, and this R1 resistance was 10 ohm. Suppose this was 30 ohm, and this was 10 ohm, and this was 100 voltage, and this was 50 voltage. So instead of assigning the branch current, so in when I'm doing a loop analysis or a mesh analysis, what I will not do is I will not assign a branch current, and also I will not apply the KCL here, but I will use only KVL here for applying it to the loops. So I'm finding a loop as a closed path. So this is one closed path which I am finding. So I'm saying this is a loop, and the loop which I am going through I will not go again. So this is again a closed path. So I can start from here and I can end up here. So for each loop I will assign a current. So for this loop I am assigning current I1, and for this loop I am assigning a current I2. So I will move through each of the loops once and I will write the equation. So when I'm moving through this loop, whatever I'm finding is this is the direction of the current through this resistance. So there is a fall in the potential here, and again this is the direction of the current here. So there is a rise in the potential when I'm moving in this direction. So it's moving from plus to minus. So whatever, I'll write the first equation like for so 10 I2. So this is a rise in the potential. So this will be minus 50, and when I come to this resistance of 30 ohm, it will be I2 minus I1, because I2 is moving in this direction and I1 is moving in this direction, equal to 0. And for this loop I can write it as, what I will come across is, when I'm moving in this way to this loop, I will come across a voltage drop. So it will be a negative 100 and plus 10 I1, and again I will come to this resistance and it will be 30, and here it will be I1 minus I2, and finally I will come across this voltage. So there is a voltage drop here, so it will be positive here, so positive 50. So if I simplify this equation, what I will get is, I will get 10 I2 minus 50 plus 30 I2 minus 30 I1. So again you can take this both together, so you will get 40 I2 minus 30 I1 minus 50 is equal to 0. And so this becomes my first equation in this case, and I'm even simplifying this. What I will get is minus 50. I'm solving this both will go together, and plus 10 I1. So this will be, both will add together, so it will become 40 I1 minus 30 I2 equal to 0. So this will become a second equation. So I have two equations in this case, and finally I could write them as 40 I2 minus 30 I1 minus 50 equal to 0, and minus 30 I2 plus 10 I1 minus 50 equal to 0. So this is equations 1 and 2 which I got. Now from this equation it's possible to write in terms of I2, and if I write that in terms of, or in this equation it's possible to write in terms of I1 easily. So 10 I1 equal to so 10 I1 is equal to 50 plus 30 I2. So simplifying it, you could get I1 equal to 5 plus 3 I2. So you got I1 in terms of I2, and you can substitute that in this equation. So it could become 40 I2 minus 30 into 5 plus 3 I2 minus 50. So when you are doing that, you will have to solve that. You will get 40 I2 minus the 150 plus 90 I2 minus 50. So this both will add together, it will become 130 I2, and this both will add together, it will become 200. So this is just a problem which I formulated myself, so the answer will not round up, so it will become 200 divided by 130, which is the value of your I2. So I2 is equal to 200 divided by 130 amperes. So again that will come in point, and once you got your I2, you can substitute your I2 in and this equation, and you will find I1. So now you have found out your I1 and you have found out your I2, and the I1 plus I2. So that's how you have found out the current, that is I1 and I2, and the current in this branch will be I1, and the current in this branch will be if you take in this direction it will be I2 minus I1. If you take in this direction it will be if you take in this direction it will be I2 minus I1, and if you're taking in this direction it will be I1 minus I2. So that's how you'll find the different branch currents. So that was how you are applying the loop analysis or mesh analysis to a circuit. So I've just computed the values, and it will find out that the I2 is equal to 1.53 and the I1 is equal to 9.59. So as found out, the I1 was equal to the I2 was equal to 9.5 and the I1 was equal to 1.53. So that's how you solve both the circuits and you found out. So again you'll see if this is possible to apply the same circuit to some other method.